Good afternoon. My name is Ian Arden. I'm chairing this afternoon's event on engineering for climate change. This is arranged by the Energy, Environment and Sustainability Group of the Institution of Mechanical Engineers. I have the great privilege of being a founder member of the EESG some 21 years ago and a past chair of it as well. We have a very packed program for you this afternoon, so I'm not going to take any further time out. But we're also greatly privileged to have not only our president of the Institution of Mechanical Engineers, but also our chief executive of the Institution of Mechanical Engineers with us in the room today. Alice Bunn is our chief executive, and Peter, his name I've just forgotten, Flinn, sorry, that was embarrassing, is about to say a few words by way of introduction.
Thank you, Ian. I have to forget my own name.
I know the feeling.
It's one of the hazards, I think, of doing sort of any form of public speaking, is that your mind, unfortunately, seems to go blank. So, good afternoon, everybody. We have in the room probably about 15 or possibly 20 people here in Glasgow, and then what I can make out, there's another 30 or 40 online. So, thank you for inviting me, and I hope I can make a small contribution to your event. I'm here today, obviously, because of the COP26 summit or conference, just for the day, in fact, and I've spent the morning walking around what turned out to be a much larger, more complex exhibition or conference than I'd ever imagined. But it is very appropriate that we should be using this as an opportunity and using it to support the work we're doing on our impact on society. And you know, what could be more powerful than engineers helping to improve our society? And in the development of our strategy, which we are working on quite actively at the present moment, one of the very key priorities is what we're calling impact, by which we mean the views that we project and express to society more generally, and to the engineering community, to government and so on. And it's very much a part of a wider strategy that we should strengthen this particular activity. It's what members want. It supports the work of groups like yours, and it supports the wider work of our technical strategy board. And generally speaking, we are trying to make sure that our institution is as outward facing as we can be. And certainly Alice and myself are taking every opportunity we can in the course of this year to project ourselves to the outside world. And in fact, yesterday we published a very short video that I did a little while ago to mark Engineering Day in the UK. So we're using COP26 very much as a rallying point for this work. So last week we ran on Thursday and Friday a conference around this subject. We're using it as an excuse almost for publishing 3 policy papers in different areas, and they have been put together and they will be published over the next few weeks. In the conference itself, we had 20 separate papers, and we had actually several hundred people attending. And then, of course, we're spending time on COP26 itself. So Matthew Rooney, who heads our policy work, is here for the full fortnight. And Margaret Enolgill, communications. I don't quite know how long you were.
2 days, this week.
Okay, so obviously Matt is the one with the stamina here.
Yeah.
So, but we are using COP26 as a rallying point, and it's been very interesting just sort of looking around and hearing some of the views that are expressed, looking at some of the stands and meeting some of the organisations who are expressing their views on this very important subject. So today's session looks very interesting. There are 3 papers, as you know. I'm looking forward to hearing them, and I hope that all goes well. So with that, thank you very much indeed, and I'll hand back to Rupert.
Thank you, Peter. Rupert Blackstone, Chair of the Energy Environment Sustainability Group at the IMechE. And I'm going to give an introductory overview of sustainable engineering to lead into the following two talks. If I can move on. I'll start by giving an introduction to the work of ESG and then define broadly the environmental challenges we face. I'll touch on interpretations of sustainability because it's a widely used word and means different things to different people. And then I'll be discussing and connecting with different approaches to systems analysis in the context of sustainable engineering, particularly thinking about climate change avoidance. And really the heart of this is what can we do as engineers to solve these problems? I'll get through the slides as quickly as I can and leave some time for questions. If you've got questions, please put them in the chat box, those of you who are remote. Well, ESG, Energy Environment Sustainability Group, have as our core objective the promotion of sustainable engineering. And one of the advantages we have as a group is that we're very cross-sectoral, covering energy, wastewater and transport, amongst other disciplines. And with that, it helps us arrive at integrated solutions. And I think increasingly we're all recognising that we need to work together, not just across sectors in engineering, but with other sectors of society to achieve our environmental objectives. We put on a series of monthly lectures by webinar, so please tune into those if you can. We produce a newsletter several times a year. We produce policy papers, for example, the energy hierarchy and waste hierarchy, and I'll come to those later in the presentation. And we collaborate actively with other IMechE divisions and groups, including on government consultations. So what is the problem? Well, the species existing on this planet have evolved on the basis of a narrow set of conditions that support life. And rapid changes in conditions result in imbalance and extinction, and this is already happening around us. And human beings have very limited knowledge about the interdependence of different organisms and are unable to predict the consequences of disruption. And a lot of what is going on is hidden from our view. For example, under our soil, there's a whole part of the ecosystem. An example here is exchange of nutrients and sugars through mycorrhizal fungi with plants, which can be disrupted by application of chemicals to land. And there's very limited but developing knowledge in this area. And that's just one example. What is engineering for? To make life easier, safer, and more enjoyable for human beings. What has gone wrong? We consume and transform more than the ecosystem can accommodate without imbalance and terminal destruction. Who is responsible? Engineers have made it easier to consume, but individual desire has driven the engineering. We are all responsible. Can engineers get us out of this mess? Engineers can help, but the technical fix many hope for isn't coming quickly enough. Stephen Hawking said, "We are running out of space, and the only places to go to are other worlds." Kepler 186f is the first Earth-sized planet orbiting a star in the habitable zone to have been discovered, but that's around 500 light years away. Now, who here believes that we are going to be travelling faster than the speed of light before 2050 when we need to reach zero emissions? Anyone? No. Well, let's say we could approach travelling at the speed of light. Who would volunteer to be cryogenically frozen and put on a spaceship and travel 500 years and wake up and start colonising Kepler 186f. Anyone here? You'd volunteer? Okay, we'll make a note of that. Make a note of that. Well, that's a possibility. And how about Mars? Talk about colonising Mars. It's very cold, average temperature around -60 Celsius, and low levels of oxygen. So the expectation would be there'd be imprisonment in an artificial biosphere to be able to survive on Mars. Would anyone here want that? Maybe some people would. We've got a spirit of adventure as human beings, and some people would want to break new frontiers. And I have to say right now, not in any way dismissing space engineering. It's very important. As our chief executive, Alice would tell us, I mean, there's lots of value in space engineering, but I'm specifically talking about colonising other planets as a long-term proposition for human survival. Wouldn't it be easier to fix our own planet? I mean, you'll note that Siberia and Greenland aren't that popular at the moment, but surely they would be better than Mars. And if we can't get people to live in more hostile environments or challenging environments on our own planet, how easy is it going to be to encourage other people to live on other planets? I mean, one idea I have had is that for all those people who have already decided to freeze themselves cryogenically, but in the hope that in the future they'll be able to be resurrected, maybe we could pack them all off to Kepler 186f to establish a human colony. But it's surely easier. These are big technical challenges, and it's surely easier to fix our own planet. What drives us to care so much about human survival, even if it means living in an artificial desolation? So there's a question about quality of life and what is worth fighting for. Now, there are various definitions of sustainability, and this is one that we support as ESG, the Brundtland definition. Sustainable development is development that meets the needs of the present without compromising the ability of future generations to meet their needs. And then the other definition below that refers to living off the capital, living off the income from our assets rather than depleting the capital. Now, those are valuable definitions, but what I point out here is they're human focus. We talk about future generations of humans and what are the needs of humans as distinct from other organisms, and possibly not taking into account of the interrelationship between humans and other organisms. And then we move on to the United Nations Sustainable Development Goals, and all very good aims there. But here you'll see the ones marked up with a person. I think it's a person with a baby, actually, rather than whale. They're the one. They're all human focused. They're all about welfare of humans. The ones with where there's a green plant there, they refer to plant life, and the green lizard to animal life. And there are a few of those that are covering plant and animal life, but very much the focus is about human welfare. And what we need to think about is how human welfare is dependent on the welfare of other organisms and how it's all interrelated. Well, there's what are we aiming for? On the right-hand side, the picture there, you could see that as a monoculture of a fir plantation. Now that's got the benefit of sequestering carbon dioxide from the atmosphere. But then some of these conifer plantations can be very sterile in terms of biodiversity. And so we're meeting environmental climate change objectives potentially, but not paying attention to biodiversity. On the other side, you've got a picture of the Knepp estate in the south of England, where they've let the land grow wild, and it's a wilderness with an ecological balance. Is that what we want? But then there's a question of productivity and feeding people. Is that really sustainable if we have that as our widespread use of land? But actually, food pressure is largely from wastage, not lack of land. So there's some sort of balance to be struck there. And then in terms of what people view as natural and quality of life in terms of their environment, is what's known as the shifting baseline syndrome, which means each generation defines what is natural in accordance with what they've been presented with at birth. So if you've grown up with lots of cultivated fields, and that is your impression of the British countryside, potentially, whereas in the early 20th century, there'd be more people who'd have seen similar views to what is on the left there. Nothing ever stays the same. So when we talk about sustainability, it isn't about a snapshot in time and freezing it and sticking with that. Our ecosystem has evolved in accordance with the changing conditions, and the ecosystem also changes the conditions, as we as human beings are doing. Releasing fossil fuels over such a short period is a shock that is hard for evolution to keep up with. If there are only a few million people on Earth, we could burn coal to serve them and it would be absorbed by the environment. But with huge population growth, that's not possible. The second law of thermodynamics, bit of engineering, the entropy or disorder never decreases. Minimizing disorder and minimization of depletion of finite resources are consistent with sustaining our existing environment. The energy hierarchy, waste hierarchy and transport hierarchy, all of which are developed by the IMechE, in which ESG were active in producing, have in common that priority should be given to minimizing consumption, thereby minimizing disorder and minimizing depletion of finite resources. This is the energy hierarchy, where the top priority, tier 1 there, is energy demand reduction, and that's something that we as ESG strongly encourage, and something Ian Arden spoke specifically about on Monday here in Glasgow. All activity requires some energy, but the question we have to ask ourselves is that activity important? And if so, how much energy is really needed to support that activity? And whilst this is a set of priorities, when it comes down to the nitty-gritty and application, there are questions of resource and economics, and there is an economic and resource balance to be struck. We're moving from priority 2 to priority 3, for example, and this could be, where do you stop insulating a building and where do you start introducing renewable heat to the building? And then moving on to the waste hierarchy. I mean, the waste hierarchy as it was hasn't been working recently in the UK. You might have been aware through the news of open burning of waste on tips of UK waste that's supposedly recycled in Turkey. That's just one example. And what's in the update to the waste hierarchy, which in Arden here has been authoring, the recycling and recovery are to be brought together, which option, whether you go for recycling or recovery, does depend on the waste type. So, for example, for metal, there might be priority for recycling. I mean, you wouldn't think of energy recovery from metal anyway. But with organic waste, then that might lend itself to energy recovery more than recycling. And then similarly, the transport hierarchy, the priority is in reducing the demand for transport in the first place. And not only is there a reduction in energy consumption, but improved air quality, reduced noise and reduced social impact. Now, how do we move from the big picture to actually implementation? Well, first of all, what are the end objectives? Where are we trying to get to? And then what potential mixes of technology and other measures could be put in place to meet the end objectives? What practical steps are to be made in meeting the end objectives? So we need to think of pragmatic steps within the constraints of our economics and societal structure. And what are the global costs of meeting the end objectives? And when we talk about costs, it's not just in terms of our current economic system, but also the internalisation of external costs, for example, mitigating the damage caused by the burning fossil fuels and the cost of that. And what are the consequences, including costs of not meeting the end objectives? And this will be, some of these principles will be covered in our next presentation with Daniel Kenning and Susan Krumdieck. Inadequate attention is given to the integration and compatibility of developing technologies with scale up, and the support in silos of different technologies, but there's not enough thought as to how all those technologies are going to fit together to meet our end objectives. And for that, national and global strategic approaches are required. And a specific example of this is matching of energy supply and demand. And these pie charts are of the UK using data from 2019. And on the left, there's the UK energy split into energy end use types. And that large slice of the pie, which is 40%, that's heating, and electricity is only 21%. So the heat energy consumption over the year is almost double that of electricity. But then on the right hand side, we've got the renewable energy supply breakdown using data from the same year, and you've got most of the vast majority of the energy supply being electricity. So there's a mismatch there between the supply and the demand. If you were to meet all the demand by renewable energy, there needs to be a change in balance. I mean, we know that heat and transport are becoming more electrified, so that balance will shift, but nevertheless there's a need to match the two. And this is an example when we think of hydrogen of different, how energy balance is important as well in deciding which is the best route for energy supply. On the top line, if you look to the top right, you've got the electricity and heat boxes, and above electricity it says 1 and heat 0.42, and those correspond to that corresponds to the electricity to heat generation ratio of a fuel cell broadly. And then to generate that 1 unit of electricity and 0.42 units of heat, upstream there are losses along the way. So there are losses in the fuel cell. Distribution of hydrogen results in more losses than for distribution of natural gas. Same for compression. And then there are losses in the electrolyzer, converting electricity, which could be from anywhere, renewable energy or nuclear, for example. And where if you see on the left, there's 2.9 in the top left box. So 2.9 units of electricity are required to produce the electricity and heat to the right. Now the lines down below, where the one below is where you've got the optimum supply of heat using electricity, which is the heat pump, and the electrical distribution required to supply the same amount of electricity as the top line and the same amount of heat. And there only 1.2 units of electricity are required. The bottom one is just when you're using an electric boiler instead of a heat pump, and even that has a lower energy input than the hydrogen route, and there's a factor of 1.4 difference. I have to say that this is just these assumptions are open to challenge. They will vary, but it's an indication that there's a big loss with the hydrogen route there. It's not to dismiss hydrogen, because it's got its role in terms of storage and buffering of energy, and no doubt it'll play a role in the future of our energy systems. Now, this is what happens if instead of just matching what is produced by a fuel cell, which isn't a ratio between electricity and heat that matches our demand ratio, we look at matching the demand in the previous charts, and the middle So the boxes to the right of electricity and heat are the balance of electricity and heat demand. And you'll need a boiler, a hydrogen boiler there to supplement the fuel cell to meet the heat demand. And then it takes you up to a factor of 3 difference between the heat pump route for heat and electrical distribution. Now, again, there are issues of storage to consider, so it's not as simple as that, but energy balance is a big factor. And this is a graph of how energy costs have varied over the last few years. And the green line, the lighter green line, is retail gas price. Now, as we know, wholesale gas prices have shot up recently, so no doubt this graph will have changed considerably. But if we're to get heat through hydrogen boilers, they're being made hydrogen ready at the moment, then this could potentially result in over 75% increase in cost, possibly more than that. And will the public accept this? So there's a social dimension to it. And then this is a graph produced by Grant Wilson, who's a member of the ESG committee, and he produces a whole suite of useful graphs. This one I've expanded there to show the middle, how the electricity demand, which is the top red line, dips in the summer, whereas if we think of the supply, I mean, currently this is the green line from low carbon sources, but if there's PV, then there's solar photovoltaics, then the peak generation is in the summer, which runs counter to demand. If in the UK, we have to meet our winter demand with renewables, that's going to be predominantly wind energy, and those wind turbines will still be there in the summer, and the output from the wind turbines won't dip as much as the demand. So there's a question there of how we balance wind energy and PV in the future and other renewables. So interseasonal matching is important. And then the biomass is very controversial. Now, what this shows is that after thinning, which is this where the green meets the red over to the left, of thinning of forests, you get greater quality of growth and greater growth, rate of growth over after thinning than you do before. So greater sequestration of carbon dioxide through thinning, but then again, there's also a habitat issue with thinning trees that needs to be taken into account. CO2 sequestration tails off as trees reach maturity, but biomass from forestry management is more sustainable than plantation solely for the purpose of fuel, but the habitat impacts do need to be taken into account. Embodied energy is an important consideration in determining the sustainability of systems. This graph is of life cycle emissions of electric and conventional vehicles, the conventional ones being over to the left there. But on the right-hand side, United Kingdom, green is the battery embodied emissions, and the purple there is the manufacture of the rest of the vehicle. And the red is the fuel cycle, so the emissions associated with the electricity in the life cycle used for propelling the vehicle over its life cycle. Over to the left with the fossil ones, they're tailpipe emissions. But you can see that the life cycle, the embodied energy here is greater than the life cycle emissions over 150,000 kilometres. So it's very significant in deciding when you switch to an electric vehicle. And here are graphs of, with the green graph is electric vehicle and then replacement after 15 years, and you get a jump in, that's in the embodied energy. And the brown one is the internal combustion engine, just carry on as normal with an internal combustion engine. And then the blue is where you start off with an internal combustion engine and switch to an electric vehicle, and you get the jump in embodied emissions there. And that jump in embodied emissions decreases with time, because this is assuming that the grid emissions are reducing to zero over the next 30 years. But what it tells you is that if you keep your old petrol car for another 5 years, you end up with comparable emissions, potentially slightly less than if you go straight out and buy an electric car. And this, with the greenhouse gas protocol, Scope 1 direct greenhouse gas emissions, for example, what gas you burn on site. Scope 2 is electricity you use on site and the emissions associated with that. And then Scope 3 are other indirect greenhouse gas emissions, so imported embodied emissions in components and products you bring to site, and employee transport. And typically Scope 3 emissions can be greater than 90% of the overall emissions. So the black part of that pint of stout there. There's a lot in the supply chain that we need to think about when determining the impact of emissions. And there are approaches to systems analysis which are useful. Life cycle assessment, the data processing for that is scientific, looking at the impact of each stage of the life cycle of systems. But the priority given to avoidance of the impacts is subjective. What's more important, local pollution, health effects, or greenhouse gas emissions mitigation? So communication and consensus are very important there. And that's to do the social side of sustainability. With a circular economy, we need standardisation and global cooperation to make that work. And there's a need to balance resource use with energy use, and the resource energy use doesn't always get taken into account in the calculations. And there's a huge amount of embodied energy in manufacturing in this country. A lot of our figures don't communicate that a lot of our emissions have been offshore through manufacture. So we need to think of appropriate technology, the scale and utilisation with consideration of embodied emissions, energy vectors. Should we be using electricity or hydrogen? We need to think about infrastructure considerations. We need to take into account there are climatic and geographical variations across the planet which will affect the measures adopted, whether there's a space for certain types of renewables and for example, and the resource available in different places. We also need to recognise cultural variations in the way that we communicate to people and different local practice that people have. Global collaboration is essential, and rather than just thinking about short-term competition, we need to be thinking about setting an example for others to follow, and that way we can bring people along with us, potentially. John Kerry, the US climate envoy in May 2021, so 50% of he called them carbon reductions, we first say carbon dioxide and ESG, needed to get to net zero will come from technologies that have not yet been invented. People don't have to give up the quality of life in order to cut emissions. Well, the rate of change in technology has not kept up with the climate crisis, which has been evident for some time. Not nearly enough is done with technologies we have available to us, for example, insulation and wind energy in the UK. Most of the world does not have the quality of life of the USA, and with a growing global population and aspirations to have similar lifestyles, there's a time bomb there waiting to explode. And the definition of quality of life is subjective. People during the pandemic have got used to different lifestyles and adjusted, and some people have been fulfilled by those, but a lot of things are returning to normal too quickly. So what are engineers to do? Design and development of technology for the environment. There's still a strong case of technology, but selection of technology that already exists on project work. We need to work with other sectors. We need to think about behavioural changes. It's hard, but it's cheap, and good communication by engineers will be valuable in this. We need to follow the energy, waste and transport hierarchies, and we need to think less about moving outside our planet and more about looking after what we've got, which has taken billions of years to evolve. And there is always a limit to consumption. Determining sustainable steps can be complex and uncertain, but it is better to act and adjust than to do nothing. Thank you. Any quick questions for the
What time do you need to finish this?
There are some in the chat.
That's all I'll comment on. Any questions from the room then? Yes.
So we're trying to wrap my brain around one particular element of electrification and in particular battery storage. And I'm trying to understand and weigh, different elements of the sustainability around that subject. Could you maybe, comment on the mining process, end of life options for batteries? I mean, we know that there's potentially some ethical issues with some of the ways that the metals are mined. We know that there's end of life options, but they're not necessarily being implemented. Electrical waste is also seems like an exponential problem.
Yeah.
Could you maybe comment on that a bit?
I'll comment a bit insofar as I can. I might invite other people to fill in who are more expert at batteries. But it's a very good point, and it is a big issue. And they do vary in terms of the design as to how much resource they use, how much mining is required, and there are shortages of certain materials. But I think in principle we should be avoiding the use of batteries as much as we possibly can for the reasons you give. They'll have a place, but if we can reduce the manufacture of batteries by demand management, then that should be a priority. So it's not just about the consumption reduction, but also timing of demand in relation to available supply. So when there are non-essential activities that can be linked to when there's renewable resource, for example, when wind is blowing, then that should be a priority over storage. But would anyone else like to comment on the batteries? Who's got more expertise in specific material developments?
I'm not necessarily an expert in it, but I do know Johnson Matthey got a huge program going about recycling lithium batteries. Huge program. So a massive engineering challenge there. And knowing quite a few engineers who work in for organisations that do big public sector and private sector installations of renewables, like solar and everything else, they are now increasingly being required, and they are looking at what they need to do to make sure that the raw materials that go into those products, whether it be batteries or in like solar panels or that, are ethically sourced. And there are companies in the UK and overseas, and that is now the engineers who are doing that. It's part of their bread and butter, is not just providing the solution to technology, but actually the ethical sourcing of it. And that ethical stance is becoming more and more embedded into the work that engineers are doing. It's not just about the technology solutions, it's about the ethical work behind that to do it. We're being required more and more to put that into the education, the training of engineers as well. I'm not the expert in technologies, but I know a lot of people who are involved in it.
Thank you.
Most of the chat consists of comments rather than questions, but and I'm not saying they're not good comments, but there's one question. I missed the reduce idea in the whole lecture. Did you want to comment a bit on the idea of demand reduction?
Yes, yeah. Well, I mean, where I was referring to it was in conjunction with the idea of increasing disorder, and it's far better to avoid any activity and consumption than to supply with renewable energy. Renewable energy is very constrained physically and economically, and it's always should be a priority to minimise demand. And that doesn't necessarily have to mean sacrificing lifestyle, but in many cases it will require an adjustment in lifestyle, which might take It might be hard initially, but something that we're all going to have to do, because there's even in a country like the UK, where we're blessed with having a huge renewable energy resource relative to other countries, particularly wind energy. We'd be struggling to implement practically the renewable energy supply that we need to meet our current demand, let alone projected demand. So we cannot avoid demand reduction. It has to be a priority, and a strong one.
Okay, I think we're going to have to,
Yeah.
for time, we're going to have to cut it there, unfortunately. Thank you. We could go on. But can we thank Rupert and the next presentation is a joint presentation from Daniel Kenning, who's here with us, and Susan Krumdieck, who's remote. Over to you, Daniel.
Thank you, Ian. Hello, I can take this off now. Hello, I'm Daniel Kenning. I'm a mechanical engineer and transition engineer, and I run Splendid Engineering. I'm also a member of the Energy, Environment and Sustainability Group of IMechE, and I'm very happy to introduce Professor Susan Krumdieck, who is online in Orkney at the moment. Hello, Susan.
Hi. Yeah, I'm a mechanical engineer as well.
You have to unmute yourself, I think.
I'm not muted.
Can we unmute Susan?
Oh, can you hear me?
Changed it so that everybody can unmute themselves again. She should be unmuted.
I'm not muted. Am I still here?
Maybe her speaker's not on. Her microphone's not on or something.
Microphone's on.
Is ours?
Our speaker switched off, is it?
What?
The speaker in this room is.
Oh.
Can you hear us online? Yes.
I can hear you.
Yeah.
So
But
if
you
put
say
it
you
next to
can't-
the microphone, you'll see the audio check, and you can have a look at that.
We're just trying to hear you, Susan, at the moment.
Oh dear.
Well, we heard there's other people who are chatting.
Where are the other people? I'm not muted. Sorry, I'm not muted.
Maybe the
Yeah, and then you
GTV.
can test the speaker at the top. Hit test speaker.
Yeah, I'm not muted. I mute.
You can turn the volume up.
Okay,
using the
I'm
bar
gonna
there.
try.
On the
All right. Any better now? No?
Just from the top bar, make it loud.
this thing here.
Yeah. Just drag it across.
And still nothing?
We can hear you now, Susan.
You
Perfect.
can. Great. Absolutely great. I'll go back to sharing the screen and see if that was the problem. Hopefully not. I'm still talking. Are you still hearing? Yay. All
And
right.
you can see your notes there. Do you want to switch off the notes, Susan, or leave them there? It's
Oh,
fine.
we got it the wrong way around. Sorry.
Wrong screen.
How about that?
Perfect. So I'm very happy to introduce Professor Susan Krumdieck in Orkney.
Hi, yeah, like I said, I'm a mechanical engineer and I'm an academic in transition engineering at Heriot-Watt University in Scotland.
And we too, and Susan and I are the co-founders of the Global Association for Transition Engineering.
Right, and in the next 30 minutes, we are going to answer the question, how do we achieve those net zero targets and take action and save the planet? Well, let's start with the fundamentals, right? Let's put forward a case for the future where the targets for net zero were met with plenty of time to spare. It's a believable thing, right? If that's true, then something happens. Something happens now that is new, that hasn't been happening yet. It breaks the business as usual plan. It results in 80% reduction in fossil fuel production and use as required by climate science. And as long as we're proposing this theory, imagine that the result of this radical change also grows our social capacity, regenerates our biocapacity, regenerates our biodiversity, and builds resilience and equity. Wouldn't that be okay?
Okay, so the facts are, if we look at the fossil carbon dioxide that is now in the atmosphere, nearly all of that got there through successfully operating and legal and profitable engineered systems. So all those molecules got there through what we do. And that's what we call economic growth. However, all the evidence, especially the evidence of atmospheric CO2 levels, shows that all the efforts since the 1960s to solve this problem, and all of the COP meetings, of which this is the 26th one, have made no difference at all to this relentless trajectory. And the industrial technical enterprise just keeps racing along the same trajectory.
Right. So the question that we wanted to answer, how do we change everything fast? That's a really good question. The climate emergency is clear. That's what these meetings have been about for more than 30 years. What isn't clear is how do we change direction and go the way that the climate scientists are saying we have to go? How do we change not only what we're doing, but the value proposition of what we're doing?
Okay, so clearly the job we have to do is to change course, and this is what transition means. It means changing direction. So we have a system, the technical enterprise, which is actually working. Everything works, everything goes fine. The trains work, the cars work, the factories work, the lights work, it all works, but it's going in the wrong direction and it's heading towards danger. So this diagram of railway points illustrates that the two things that we engineers have to do is to, first of all, get off that track that we're on, because that leads to danger. And the current trajectory lacks the all-important capacity to continue. It cannot continue. So the first thing we need to do, disruption, get off that track. And then the second thing is to identify a new trajectory and a new way. So that's the two things we're trying to do to get towards safety.
All right, Daniel, that sounds great. But every one of those changes that you want to make involves changing what we're already doing that works and changing what uses fossil fuels. And every time I work on one of these problems, what happens is that we understand it to be wicked. A wicked problem is when you're not trying to change in the way we have been for the last 70, 80 years, which is to make things bigger, make them better, make them faster, less expensive. We're trying to change something that already is all those things into something that uses 80% less fossil fuel. And the wickedness of it is that it already works great. Now, of course, we know it's not sustainable, and it's not even that hard to figure out what's not sustainable about it. It uses more fossil fuels than we can use right now, right? But there's a really big problem here, and that's that we are meeting our needs with this thing, and the people meeting their needs don't know how else they would do it. And so that is going to stop our discussion pretty quick. But, you know, the scientists and environmentalists, they're going to come up and say, you know, that's causing so many problems. And again, we'll get stuck just looking at the problems. So we know we want green solutions, but we don't really want those green solutions to be about change. We just want something to relieve this pressure of the need for change. And we don't want to even think about what would happen to our essential activities and goods, because even though they might be able to be met, we don't know how. And so We want to use what works great. So we get caught in this spinning wheel of death, really. It's like when you ask your computer to do something it doesn't want to do, it just spins. And that's where we're at with wicked problems. And everything that uses fossil fuels is one of those. And so it's really the first step in transition engineering is to understand when you've got one of these wicked problems, sit down and parse this out and recognize there is no quick solution to this. You have to do something else. This is a complex, wicked problem. It's got lots of parts that intertwine. It's tied up with other systems. It's complex. And so answering that question of how do we change everything quick? What we know about wicked problems is that 1,000 reasons why you can't change it right now will fly up and stop progress. So.
Yeah, so as Susan says, so the thing is that in the past, massive changes in the industrial technical enterprise in systems that were not broken, that were working, massive changes have happened in the past. Lots of times. For example, in 1911, the whole industrial technical enterprise was working just fine, but factories, vehicles and products were dangerous. They were unsafe. And every year, 100 and so years ago, thousands of workers died at work. And at first it was accepted as the price of progress. It was accepted until it wasn't accepted. And when it wasn't accepted in 1911, engineers got together and effected the emergence of a new discipline, which we now call safety engineering. And because of that engineering initiative and that emergence of a new discipline, which you can call a corrective discipline, thousands of lives are saved every year. And that happened over 100 years ago. So it can happen again.
That's right. If safety engineering hadn't happened 100 years ago, if you stayed on the same trajectory of worker deaths per unit of industrial good, you would have 8,600 worker deaths a year now in the UK. Today, there's less than 200. Those 8,600 deaths that would happen without safety engineering occurring would all be just the price of progress, things we couldn't change because, well, what would you do? And now those 200 deaths are not acceptable. So something really changed, and it was safety engineering. Safety engineering is the first really solid instance of the emergence of a corrective transdiscipline. Okay, you all know what corrective means. A transdiscipline is really interesting because it's not its own discipline. In a way it is, but it's also a discipline within every field. And every field has its own ways of expressing this thing of safety engineering. Now, safety engineering started in 1911, as we said, and it started with 62 mechanical engineers who got together after a terrible incident that killed 140 young girls in one day, the Triangle Shirtwaist Factory fire. And they decided to just do their job, but not kill people. And they decided that in order to do that, they would have to be honest about what the problems are and what the possible solutions were. And to me, to think about what was going on at that time in 1911, that they thought the most important thing that they as engineers could do was to be honest, that really resonates with me as somebody who's worked on hydrogen and carbon capture and things that, you know, I want to be honest now. I want to tell people what the probability of that working is. And I want to be honest about what the problems are. It's that we're burning too much fossil fuel. And I find those two pieces of honesty quite hard. I don't know about the rest of you. The other thing that they decided was to prevent what's preventable. All right, I'm showing you this picture of linesmen doing their job in a very profitable industrial technical enterprise. And the rate at which these linesmen were dying on the job was faster than the rate at which they could be trained. So this was not a nice place to work. And safety engineering wrote down this nice phrase, prevent what's preventable. All right, you look at those guys and you think, what's happening? Well, they're getting electrocuted and they're falling to their deaths. And if you look at what a linesman looks like today, you'll see that the engineering that was deployed to prevent what's preventable isn't something you had to go to Mars for. It was normal, everyday types of engineering, materials, mechanics, dynamics, power engineering, physics. All right, they deployed engineering that they could immediately to prevent what's preventable. And you know that there are a million of these examples of engineering in practice. Yes, there's some research. Yes, there's some experts, but there's transdisciplinarity. There's everyone thinking, how would I prevent that? How would I do this? What could I do about this? What could my company do about this? So the idea of safety engineering is to do your normal work, but with the duty of care for workers' lives and health. And that is not a surprise to us anymore, but 100 years ago it was. It changed really fast though. Safety engineering grew so fast. And this ethos of changing successful systems that work very well, thank you very much, if they must be changed, that was applied in all fields within about 30 years. And it was a sticky idea that kept going.
So this diagram here shows, this is an inspiring model that shows that the principles of safety engineering on the top line there, they were developed, I think there's some dates on that diagram as well, isn't there, Susan? I think. That's it. So in 1911, safety engineering was developed. It was developed by engineers. It wasn't actually developed by politicians setting targets that the engineers followed. It was the engineers leading. And they just set out to apply the principle that Susan has mentioned of just doing what needed to be done without people dying. And this similar process has happened over history. Every time a big successful system turned out to be disastrous, either for people or for the environment. So what we're doing now is proposing a new corrective transdiscipline, which we call transition engineering. And this is the way to make something really big happen right now, and quickly, that will change the industrial technical enterprise. So we have this method to do what needs to be done, but with 80% less fossil energy.
Right.
Back to you, Susan.
Yeah. And so I think you're all maybe along with us at this point because you're aware of all these transdisciplinary fields of engineering. You're aware of what they do, how many lives they save, how many disasters they prevent, how they improve resilience. And you're thinking, well, yeah, could that kind of thinking be applied yet again to the biggest disaster we've ever seen so far? We think so, and so if you want to be a part of this, probably the next question you're asking is, okay, how do you do that? And our answer is relatively simple. You use a method. All right. If you remember, there's things like free body diagrams. There's drag relations. There's all these methods that we use to do hard things in engineering. And for about 20 years, my research group and others around the world have been working on, okay, how would you do this? How would you engineer change where change is not actually wanted, but it's warranted? And the answer came out of all that research, published journal papers, more than 50 papers, and working with Daniel and others in practice to see, okay, how would you apply it? How would you do it? And the methodology is called the interdisciplinary. Remember, we said it's transdisciplinary. Interdisciplinary transition, because you're going to change something. Innovation, because how you're going to change it isn't actually known right now, or you would just do that. Management, because it has to make money, and engineering, because it's an engineered system that has to change. It doesn't matter what your carbon tax is, an engineer still has to do something. All right, so the methodology has 7 steps. Why does it have 7 steps? You can read the journal papers and find out. It has 7 steps because it works. So if you imagine that you're faced with one of these wicked problems and it has no solution, it's horribly complex, and at every turn, people just actually don't want to talk about this anymore. They want to go talk about some cool technology they saw on the internet. Okay, can we all get together, stakeholders in this particular project, in this particular problem, and let's go back and look at history. So step one, we look at history. Why? Because there's not that many arguments there. We can all learn something, and we can learn together and start to build our stakeholder relations around finding out, has this wicked problem always existed? 100 years ago in 1911, did they have this same problem? How did they meet their needs? What were the businesses like? What were the policies like? And we just find out. It's not a judgment thing. We're just learning history. And then we start looking as we come forward in time, what changed? How did those changes affect things? How much of it was engineering change? How much was social change? And what we'll start to see by looking at past dynamics is how this system works. And it works that engineers change something, people use it, policymakers regulate it, somebody in business sells it, and engineers change something again. So really, when we change something, the rest of the system adapts to it. Therefore, we can change something in the way it needs to change and know that everything will adapt to it. So we then study, okay, well, what's going on at the moment? Get good data, get good information, get facts. That's the present study. Then we look forward a little bit to see, okay, what do we think is going to happen next? What are the stories people are telling? What are the ideas they've got? And we test those out with engineering analysis to see, do they actually solve the problem? Or are they part of the problem by being distracting? If we find that the things that keep stopping us in this wicked problem, the green solutions we're hoping for, but that just never come, are really part of why we can't solve the problem, then we need to just set them aside, park them for a while, and we'll come back later. Let's get innovative. How do we get innovative? We apply the constraints that we know are the requirements, and then we take a little time travel. Now, that's a whole skill. If you want to know more about it, you can learn easily, but it's the funnest part. It's not like visioning. It's an engineering visit to 2121, where we see that that wicked problem has indeed been solved, and how are people getting along doing stuff. And that lets our problem-solving brains go off the chain. Then we come back, do backcasting, you know what that means, and then we design a project. And this is where we use the insight that we got from this whole project. We use the perspectives of all the stakeholders, and we develop a project that we can do in the normal way that changes the direction. There's our transition mechanism of how we change things. Now, there is one more piece, and that's step 7, which is to look forward for unintended consequences. We're going to do that this time because, yeah, good step to include. All right, so that's our method, and I don't think it's too complicated, and it's quite colorful. So you think you could do that?
So there you are. You see, that's the method. We've got this methodology, and this has been developed over many years, 10, 20 years, as Susan was saying. And we've been asking ourselves for 10 years, how can engineering help bring about change to unsustainable systems? And we've been asking, how do we take action? And as Susan has mentioned, there's steps you can take. And I promise you that diagram, it might look complicated, but the 7 steps, after a while, you'll memorize them. They're easy to remember, and it makes complete sense. So we've been working out how to answer the questions of how to achieve sustainability or the capacity for continuity by getting the correct problem definition, exploring the history, creating a new way, as Susan said, time travel into the future, and collaborating with all professionals and academics. And these are things that you can all do now. Everyone on this call can do those things right now. It's not difficult. So it's something that can be done now straight away to deliver. If I pinch the words from David Attenborough, this is what can be done to turn the tragedy into a triumph, and it can be done quickly.
Right. I agree, and we're going forward, and we're bringing as many people as we can with us. There's a fundamental method, there's tools, there's approaches, there's you know, economic analysis that's quite different, and that's all been published now in the first Transition Engineering Handbook, and that came out just before COVID, so it's quite new. And there's ongoing research into more transition tools and methods, and that stakeholder process that we talked about. It's worked so far, but we want to get better at it. And that's why I'm at Heriot-Watt University, because we're setting up a master's in transition engineering, a research program. And actually the research program is to achieve the net zero transition in the Scottish Isles by 2030. So we're gonna just get stuck in there and do this. That's what we believe. We can do this. There are already management and exec ed opportunities possible for those processes for leaders and for teams. There's already online courses in transition engineering that receive micro credentials and CPD credit. Daniel's offered CPD around the world, and there's, like I said, already online. And some folks in the UK have done a lot of work, and they've set up a actual professional organization. The first one's that is transdisciplinary. And it's called the Global Association for Transition Engineering. And we invite everyone to have a look at that. And there are engineering consultancies in transition engineering, and a lot of engineering consultancies that are, especially their young engineers, sponsoring them to take these courses, get trained, and start working on transition for clients.
Thank you, Susan. And I think that is, yeah, I think that's the end of it, end of our talk. So basically, there's tools there available, and basically all of you listening and all of you online, you can do this right now. So it's there to be done. So please join us.
Yep. And it doesn't matter which field of engineering you're in, you can work on changing what needs changing in your field by becoming a transition engineer. And why do we think, okay, when we set up GATE, it was funny because we thought there needs to be another thing, another organization, another, action group, like we need a hole in the head, right? Another action group isn't going to change anything. But then when we started thinking about what transition engineering really is, that it's another one of these transdisciplines, that if we didn't start it, the first 62 of us that got together, if we didn't start it, we're going to just continue going to the future we don't want to go to. So because it's a transdiscipline, everyone can become a transition engineer. It's not an elite group. It's not an outside crowd. So yeah, thanks for listening to our explanation.
Well, thank you very much. Very useful and interesting talk. It occurs to me that we hear a great deal at the moment about the energy transition. It seems to be one of the most popular buzzwords of the day, but we hear very little about how that's going to be engineered. And so transition engineering obviously has a very major role to play in this. And I think it's absolutely appropriate that we are highlighting it in this event. So thanks again for that excellent presentation. Any questions from the floor?
Yeah, I've got one. So first, great presentation. Thank you. Very slickly done. Good tag team there. I quite like that. It was a nice effort. I've been interested in energy transition and peak oil for 15 years or so. I've been first into it. It's a really, really depressing subject when you start getting into it about, you think, what needs to be done, human behaviour, and the capability or not of our politicians. So one for you and Susan, what gives both of you hope that we can actually do something about it?
Well, I would say because the examples that we've worked on together, well, and separately and together, we've both got examples where the results have been possible. And one example, shall I tell them about the no-fly conference example?
Well, I put up the data there if you want to.
There you are. You see, there you are. You see, you might say how the COP26 meetings. There have been 26 meetings with people flying in. And there's the specific wicked problem, which is the problem of climate campaigners flying to climate conferences. And that's a very specific problem. So Susan was working ages ago on this idea of how to not fly to conferences. And the idea, the no-fly conference, is not just about clever video conferencing technology, and it's not just about going by train, because then you don't gain all the things you gain from a conference. So if you look at what you gain from a conference, a lot of it is about being in a room with people, as well as listening to talks. And it's about going to a meal afterwards with people and meeting new people, building trust. Lots of human things that aren't to do with listening to a talk. So in the no-fly conference, I don't know if it's there, you have a room in every country where the local people go and sit in the room and meet each other and eat and drink together and talk to each other. And then you have really good video links like this one in between countries so that you can listen to the talks. And then an even cleverer bit is, because of different time zones, you have time travel. So you have a big time machine. No, you don't. You use logistics so that some people are sleeping. If you have a global conference, you can have a schedule so everyone sleeps and everyone gives a keynote when it's 10:30 in the morning for them, and then everybody has an evening meal when it's 8 o'clock in the evening for them, and you can get around it that way. And we made a proposal to the COP team to bring that, to demonstrate here, and we couldn't bring it here. Maybe we'll bring it next year. But that would allow you to get all the benefits of a big conference like this with no flying, and you immediately hit your 80% target much more easily, in fact, than redesigning the engine on a Boeing 737. It's actually much easier engineering than the traditional way. Yeah, with bigger results.
It was actually a really challenging design problem, I have to say. And it was hard to overcome the wickedness of that. You just can't change this thing. We like our international conferences, but I'll tell you what, once we've done a few of them now, we've done 4 now, that not having to fly, maybe everybody's now learned that in COVID, that the time and the effort and the money you save in not flying, and you still get this benefit of an international conference. Yeah, it just, the reviews or the feedback from it was that it was much more preferred. And that was actually published in a paper in Social Business, in the journal Social Business, with all the details of the design.
And there are lots of wicked problems like that. And every time you look at a wicked problem, and all you do is you bring the wicked problem into the doctor's surgery, and you sit down on the table and put on the doctor's table, and you check out the problem, you find out what the real problem is, you address the real problem, you apply the methodology, and you get the answers at the end. And it works with every system. Okay.
Great. One of the participants online is our former Chief Executive of IMechE, Colin Brown. Hello, Colin.
Hello, Colin.
Good to have you with us. So we better let him ask his question, which is, in the past, IMechE talked about mitigation, adaptation, and geoengineering. Is there a role for this in transition engineering?
Oh, I love this.
That's a good point, because I think in that context, the use of the words mitigation and adaptation were used differently.
Yeah, and okay, because we said we work on wicked problems.
You've got an answer, Susan, then.
Pardon? If you already know a thing you want to do, then just do it. Right?
You froze in there, Susan.
Pardon? Oh. Am I muted again? Sorry, I'm just going to stop sharing and let you all go on.
Hi, Susan, I can hear you perfectly.
Oh, okay.
It's a room in Glasgow that's disappeared. I can't see or hear them.
Yeah, they froze up, unfortunately.
Yeah,
but I've stopped sharing, so maybe that will help.
It's the Glasgow has got a problem, I think, not us.
Okay. Yeah,
Susan Lawrence here. I just have a quick question for you.
sure, as long as we're all here.
Very fascinating. As you know, I'm very interested in transition engineering, especially in terms of its applicability in developing countries where there's a need for transition. Although how we define transition in those contexts might have to be looked at again. What do we mean by transition in a developing country context?
Yeah.
However, having said that, I think there's clearly a need to build capacity in this very important field for developing country leaders, engineers, community leaders, people who can actually be part of the process of facilitating the transition. So I wanted to ask, do you have, can you share any experience that you've had so far in working with developing country, say universities, to as instruments for, or as places where capacity building in transition engineering can be realized?
Well, I've just been really lucky to be able to do research, especially sort of energy and society type research in developing countries in different contexts, Africa, South America, Maldives, and the Pacific. And what I have to confess is that mostly I just learned stuff by working with people. I really just wanted to learn. And I think that learning has gone into that methodology. And when we had our last conference in New Zealand, and Maori engineers were there, the native New Zealanders, the indigenous New Zealanders, they said, you know what, that's how we would do something. So I think I might have picked up a little bit. And you're right, the work in what I no longer call developing countries, much more honestly, post-colonial countries is a better explanation. That work, you're right, they don't have to change what they're doing. They may, or maybe in a way they do, because they need tools to say, well, here's what we want to do. Basically, that's the change they have to be facilitated to make. And my most recent paper, I hope, makes a big contribution to that. All right. Do we know if Glasgow's back? Yay!
On time, we'll need to close it there.
Okay, thank you very much.
Thank you very much, Daniel and Susan, for that very interesting presentation.
Thank you very much. Thank you.
Well, tea should be ready. Not recording.